So our first equation is going to be conservation of mass. So here is the simple form, which is simply that my mass flow rate in minus my mass flow rate out lets me figure out how much the mass inside of my control volume is going to change. Now, before we can actually do anything with this, we need to actually figure out what our control volume is going to be. And there's two ways to do this in Aero. Because, for thermodynamics, for other courses, you just say, okay, well, it's my cylinder, my container. But I'm flowing through the sky. Like, what section of the sky is my control volume? So how do we do this? Well, there's an Eulerian viewpoint and the Lagrangian viewpoint. So in the Eulerian viewpoint, on the left, we have a box, just a particular box in space that we care about. And we're seeing how the air flows into that box and out of that box. And this is not a literal one, this is a imaginary box. So I draw a boundary, that boundary stays stationary, and the air then flows into it. And so that means that my flow properties are a function of where they are as well as time. The Lagrangian viewpoint is different. In that case, I look at a particular fluid element. It's like I cut out a little piece of the flow and I move with it. And so as its properties change, I can measure those. Now, for the sake of sanity and because it makes a lot of our equations easier for this class, we're going to be using the Eulerian viewpoint. Now, if we use that, we can then start looking and seeing how air flows into and out of a box. So here's the equation. This is conservation of mass for air, and for any fluid, honestly. And there's four terms here, each of them with a partial derivative. So first off, what you'll realize is that the first three terms are simply saying what is the difference between the air that flowed in, my mass flow rate in, and the air that flowed out, my mass flow rate out, in that particular direction. So I do that first in the x direction. I do that in the y direction. And I do that in the z direction. So with each of those, I'll find possibly some difference. I might have more mass flowing in the x direction and less flowing out. But in the y direction and the z direction, it might be different. And so if there is a difference in my mass flow rate into my control volume, well, what will happen then is I will have a change in the density of my control volume. So at the beginning, I have, however much air in there. At the end, I'll have a different amount of air inside of it. So this is conservation of mass. This is the basic equation here. Now we can simplify this. Like I said, we're going to be simplifying things a lot. And so how do we simplify it? Well, it's not terribly hard. We make an assumption. And we're going to assume for most of this class that our flow is incompressible. If it's incompressible, that means the density is constant. And this is great for slow air. So if my Mach number is less than 0.3, I can make this assumption. Why? We'll find out why that later, but it's mostly because airs are really small then. And then it simplifies because all my densities come out of their partial derivatives, and I get this simple equation, which is just in terms of velocity. If I want to, I can write that compactly as the gradient with the dot product of the velocity should equal 0. You'll see this a lot, so you should get used to this little form right here. Okay, that's it for this time. Thanks for listening. I'll see you all later. Bye-bye.